All right, so we'll start with our next content here, intro to the PE file format. Again, the reason behind it, it's not just simply for the first project, which is going to be to parse a PE file. We'll talk more about that next week. But also just to talk about some of the processes that happen when we build files, when we load them into memory, when they actually are executing, because there are considerations that we need to take in place, I think, deepen the understanding so that when you're going through the reversing process, you understand better what's going on. Like the previous lecture, this isn't just PE. I want to talk about a couple of things, some additional topics that are related. They're not exclusive, though, to PE, that I hope will help shed some light on not only talking about the PE file format, but also when you start doing some disassembly reversing and you start seeing commands or instructions inside that disassembly that may or may not make sense. Because remember, compilers do things that we don't necessarily expect. As far as PE then, what is PE? Not just a fun time that we used to have as kids. It is the portable executable. 2 lame jokes in one day. I'm on a roll. I do get PE though now having kids again. I play horsey more than I ever thought I would. And what does that involve? That involves me crawling around on my hands and knees with 2 little children jumping on my back. Maybe I should have had kids when I was younger because it's a lot of work. So it's a file format. And again, what we're getting ultimately with this is the ability to generate that source code into something that we can execute. There is another step though. And one of the PDFs that we'll go over that I provided for the lab goes a little bit more into loading. This, again, piggybacks with a lot of what we talked about earlier. Any one of these slides, any of this topic, we could really spend a lot of time on. Right? We could probably take any slide, talk about it for an hour, spin it off into a course. There's courses on compilers. Right? Do we have a course here on compilers? You build your own programming language. Maybe you cover some of that stuff there. Yeah. Okay, I mean, you could spend a lot of time with this stuff. So the idea here isn't to go so in depth that you understand every single piece, but hopefully you get a much deeper understanding of how it works. The last step, and I don't remember how much I have in the slide deck, but is the loading process. So what happens when you run that executable? It has to be loaded into memory. And what the PE file format allows us to do then is it allows the operating system, in this case Windows, to take that file, to figure out where to start, and to load that into memory. So it loads it into memory, it knows where to start, it starts executing instructions. That's basically what it's doing. The PE format can be used for a variety of things. It is Microsoft-centric. It includes DLLs. And so one thing that's nice about learning the PE format is that it also helps if you're having to analyze some DLLs. DLLs, dynamically linked libraries. So if you're creating a library to share with other people, if you're looking at particular ways in which you can try to infect people, maliciously with DLLs, it helps because you're kind of looking at the same thing. In fact, I think there's just one bit inside of one of the headers in the PE format that differentiates it between an application, a GUI, a console, and that DLL file. Here are both of the file format layouts per Microsoft's PE/COF standards. So you can see on the left's PE, on the right's COF. Don't worry too much about the COF. PE is the one we want to focus more on. But kind of looking at the different sections, the different information, you can see some overlap there. We're going to get more into this structure. Right? So this is just to introduce exactly what we're looking at here, to start thinking more about how is a PE file formatted. We're going to come back around to it though and get a little bit more detail here towards the end of the slides if we have time today and go through some of those. So we have some junk, MS-DOS 2.0 compatible stuff. We got the magic number, we got this DOS stub, and for the most part you can ignore the DOS stub. You've probably seen the DOS stub if you've opened a file in a hex editor and seen the text of this program cannot run in MS-DOS mode. From there we typically jump to the PE header. Right? That's really what we want to look at. That's also what the operating system is going to look at, because the PE header gives us information about the sections, and the sections then contain things like code, like data, like resources. That's where it's going to find all that stuff that makes it run. COF, very similar. There's a header, there's the sections, very similar to these, and then the different sections, which aren't always going to be the same. You'll see there's a debug one in there, which can provide information about the debug process if left in. So very similar, but not identical. All right, the first aside that I wanted to do was to talk about data alignment. Have you guys run across data alignment before? Okay, what is it?
So like aligned by like 4 or 8 bytes, depending on how large it is, just that way everything lines up and it's not all over the place.
Okay.
If you have like good examples like a struct in C, if you have like a character and then an int, they're still going to be byte-aligned every 4.
Yeah, because how many bytes is a character?
1.
Typically 1, right? And then we already decided was 4 on most systems, right? It is platform dependent. Yeah, so the thing that you'll run into a lot is this alignment, and you run into a lot with memory, addressing, spacing, the way that the stack is aligned when you look at the stack or a function call, prologue, epilogue stuff from 314, is that it all boils down to a level that I know nothing about. That is the electronic level, or how memory is actually laid out and how it's accessed. But from the software level, what operating systems typically access memory in chunks, 2 byte, 4 byte, 8, 16, 32, whatever that size happens to be. What helps then is if the alignment of the data matches the size in which the read that chunk size is. Because of that what you just said right there, it depends on those address sizes. It's kind of like a hard drive, right? If you get a hard drive that's very fragmented, you have files that are all over the place. It typically takes that system, at least in the old days, a spinning disk. I know solid states are probably a little different now. It took it more time to get all of the bytes for that file because it had to physically move the read and write head around that platter a lot more. The same thing can kind of happen here, and that if we can read the data, if we read in 4 byte chunks, and we have data aligned on 4 byte boundaries, then one read gives us those 4 bytes that we're looking for. We can load a pointer, we can load an int, we can get a char, we just have additional space we don't care about. If we don't keep that alignment, then what will happen is we have to cross that boundary. So now if we have data that's spread across that boundary, it's not aligned, we have 2 bytes in one and 2 bytes in another, we have 2 reads in order to actually get that information. So you'll see, even inside the PE header, in the file systems, inside the stack, there's a lot of alignment that you'll see it, you'll read about it, you'll maybe have to figure it out at some point in time. The padding is the other thing, and it's exactly what you said, in that you may have padding in order to maintain that alignment. You may create a struct in C. Structs have members, members have types, right? Because C is a typed language. So you have ints and chars and shorts. Not everything is going to be 4 bytes. And so what you sometimes will see, or oftentimes you'll see, is that I don't know if you did it in 250 or in any other class, but you had that size of. You could say size of and something, and it would tell you how many bytes that it requires. So typically when you malloc, you say malloc size of to give you the correct bytes that now is kind of platform independent or architecture independent. With structs, you could sum the members, but that always and typically wasn't the actual size of the structure. And that's because of the padding, right? Because what the compiler will do is help to ensure that that struct and those members stay on that particular alignment, 4 byte, 8 byte, whatever it might be. So you might get additional padding. These are the best pictures I could find without making something myself. This concept here, or what this is, maybe I'm beating this up a little bit too much, and we can move on. But what this is trying to depict is if each one of these images has 1 byte chunk, 2 byte chunk, and 3 byte chunk in which we're accessing memory. This also then looks at 1 byte alignment. So if we have 1 byte chunks that we're reading with 1 byte alignment, then to read 4 bytes, it takes 4 reads. Same thing then if we read from a different address, right? Because it's the same thing. Now, if we move that and say that we want to read 4 bytes, but we read in 2 byte chunks, in this particular address, it works fine. Right? We have 2 reads to get those 4 bytes. But now, if that data happens to become misaligned, then it might take 3 reads in order to get those same 4 bytes. And then same thing here with 4 bytes. If we can read 4 byte chunks, memory is aligned on a 4 byte boundary, we can, with 1 read, get those 4 bytes. If it's misaligned, it's going to take 2. So we doubled the number of reads that we needed in order to access that information. All right, so this is an example, we went through all that, so I'm going to skip over that so we can keep moving. This is really pretty much the same example that we just got done talking through. So instead we've got some code in C. You can see that I'm not doing a structure, but I'm declaring these variables here. What is the size of a short? 2 bytes, yep. So 2 bytes, what's the size of a pointer? depending on, yeah. And then what's the size of your int? 32 bits, right? So what we see then, because we start, this is main. Main's a function. So when your program executes and you look at that in IDA, you're going to see that it has a call stack. So it's going to have a stack, and you're going to see that these are what? Local variables. So the space for these is going to be allocated on the stack. What is this here? Push, move, and sub. Yeah, it's your prologue, right? So typically your prologue. You set your base pointer and then your stack pointer, and then you subtract from ESP the number of bytes that you need in that address space for your local variables. If we said this was 2 bytes, what did we say that was? 4 bytes? Or 8? 8 bytes and 8 bytes. What does that give us? 16, 18, right? And how much space is allocated on the stack? Eight, 4, 32.
Should be 12. Yeah, like C is 12.
What's that? No, it's right. It's right.
Why are not 8 bytes and 32-bit?
What's that?
Is the pointer 8 bytes and 32-bit?
Well, now I'm questioning myself. Is it?
Yeah, too. That's how it was.
I thought- 64
I think it's 4 bytes, yeah.
64, it should be 8 bytes.
Yep.
Okay.
Yep. So make the wrong math. So the point is, we should have 2 bytes, 4 bytes, 4 bytes, right? So 8, 10. That would be, we only need 10 bytes in order to get these variables. But what did the compiler do when we disassembled that? It allocated 12. 0C hex is 12. So we got 12 bytes. The subtract from ESP 0C, right? We have our stack space. So that's subtracting ESP. ESP is a pointer to the top of the stack. So we've moved that pointer down, that's allocated space on the stack for those variables. But it did 12 bytes. So it's allocating in effect here 4 bytes for each variable instead of only 2 bytes for that short. Right. So it might do things that you don't expect. It did that though in order to maintain the alignment. So I wanted this to be, hopefully I didn't confuse anyone, but I wanted this to be something that's a little more practical, because you're going to see this every time you disassemble a program. You're going to see that this number, stack allocation, might not match up with variables that you have. So if I said, looking at this code here, what are the variables that have been allocated? Could you tell?
You can tell that there were 3 variables allocated.
3 variables, yeah. You won't probably know unless you look at the rest of the disassembly. Since this is a short and there is a value of 0 in it, somewhere in here you're going to see a move into probably, what do we say, 2 bytes. So, AXAL, the value of 0. You'll see that the way that the data is used, we're using a lower part of that register, that 32-bit register. So that's how you start to get better insight into what that type actually is. Otherwise, it's very hard. We don't always know, because all we have are some space that's allocated, bits and bytes that are allocated in that address space.
You got me all confused about 20 seconds now.
I know.
I used to think about 32-bit.
Let's look it up, because
I'm pretty sure.
I don't know why I just completely derailed myself there.
I could have sworn it was 8.
Well, 1 byte is 8 bits, 2 bytes is 16, right?
Yeah. 4 bytes is 32.
4 bytes is 32-bit.
Okay.
So your 8 bytes would be a 64-bit, right? So we were that is correct. It's easy to get. I find it even to this day. Not that I've been reversing for a long time. I haven't, but I find it still easy to get my mind twisted and out of discombobulated and throw myself off, confuse myself every once in a while. So hopefully I won't take any of you guys down with me, but it might happen. All right, it's not intentional. I don't come in here thinking, all right, what can I screw up today? Well, there's plenty to do that too.
We just stopped talking about 32-bit. How about that?
I just move on. That's the other thing. Is I just find the least awkward way to transition off that content and move on to something else. You guys got it, right? All right, let's move on. Perfect, good. All right, so we got about 10 minutes. I am starting to sweat profusely. So let's get through a couple more slides here. Portable executable. So we've been spending all this time talking about things I hope you find important or interesting or adding some insight into this whole process. We can talk more about the portable executable now. You can see here, this is a pretty good diagram as far as generally speaking, conceptually, this is what the PE has. We have the MZ header, which is our magic number. We have the DOS stub, which is that this program cannot be run in DOS mode, which is for whatever reasons just something that Windows, Microsoft continues to carry on because I don't think you can even run things in DOS mode anymore. I guess I'm not sure. I haven't done it in quite a long time. You have the PE header. PE header is going to be important. And the way that we're going to have to tackle this parsing a PE file is we're going to, again, we have a file and we have a bunch of binary. And so we have to be able to figure out how do we get to the header. Once we get to the header will contain information about the section table. When we get to the section table will contain information about the individual sections, right? And so we can follow links. We're going to use structures and pointers in order to do that, and that tells us everything we need to know about that actual file. So the sections that are commonly associated with your PE files, it can vary. Typically there's at least two, as you can see on the slide. There's a code and there's a data. Code is going to be for what is executed. Data is going to be for things that are essentially read-only. It's actual data. It's the global variables typically. There are other sections though, and depending on what PE you parse or what the purpose of that file, that executable is, you might have different sections. You might also have, depending on the compiler you use, sections that are called different names. As far as these names go, so the section names, text, code, data, BSS, RData, .data, maybe you remember some of these from 314, resource, eData, iData, all this stuff, right? That's just there for us as the human being to read, oddly enough. It really doesn't have any impact on the actual section, right? So, but that tells us what the section should be used for. Text, code, like I said, text and code, data is going to be data. Resources, right? So if something's packed, it might put the executable packed inside of a resource. You might have the icon, like when you used to actually download and install software, you got the desktop icon that came with it that inherited not the default. Like with PDFs, you can do that, or with executables, anything. It's the actual icon that it uses. So you can embed an image in there, and then when that program is dropped on your desktop, it'll use that icon instead of whatever the system defaults are. Import section, export section, debug information, all things that may or may not be helpful depending on what you're trying to do, particularly import and export. And we'll spend some time here throughout the course talking in more detail about those. What happens when we run a program? Right? We load it. The loader, the operating system loader, is responsible for taking that thing on disk and getting it into memory and beginning execution. So what happens is that there's a mapping process that maps that file, that image, puts it into memory. And typically with a PE file, what you'll find is that the layout that you see on disk is pretty much identical to what you find in memory. So if you had to parse a running process or a PE there, if you found it on disk, you can find it while it's running. It's not always the same though. So some of the things that can make it different would be some of that dynamic stuff that we talked about. Malloc calls and stack allocation and buffers and arrays and things like that. Because defined in code, we don't have to have 50 bytes available to have a 50 byte buffer, right? But when we actually execute it, now we need that memory made available for that particular buffer. So it may not be, it'll be, for the most part, unless something malicious is going on, it'll be essentially a one-to-one mapping, but it may not be the same size because things are going to be actually executing now and those dynamic things are going to be running. All right, I think this will be the last topic for today. Concept of virtual memory. And this is another one of those slight deviations, but I thought was worth taking some time to talk about because we're worried predominantly about addresses. When it comes to parsing, when it comes to running, when it comes to disassembly, we're worried about addresses. Operating systems, most of them, a lot of them, I don't know, they use virtual memory. And virtual memory, I used to think when I was little that virtual memory was just you run out of physical RAM and you start writing stuff to the disk. And while that was kind of true, it was a pretty naive view. What virtual memory is it's a mapping of a virtual address space to a physical address space. And what makes this very beneficial There's a variety of reasons, but some of the more important ones are that with a virtual address space, you can have a contiguous block of addresses. So when you have an image base, and again, we'll talk about this a little bit more. When I say I'm going to load the beginning of my file here, and this is how I find the functions because of these offsets, it's a lot easier to find those offsets, to find those function calls, because we have a contiguous block of memory. What happens when we malloc? We get a contiguous block of memory, right? What if we define an array and we didn't get a contiguous block of memory? Because that's what arrays give us too. One address after another for the size of the array. If we didn't do that, it'd be a real pain in the butt. Either the programmer would have to deal with that, which would be almost impossible, or the program at runtime would have to deal with it, which would also be very, very difficult. Right? So some of the benefits, we get memory isolation, hopefully. Right? So it has its own virtual address space. We have this thing called paging. And paging is what allows us then to swap out and actually use secondary storage in conjunction with primary storage in a way, theoretically anyway, have more memory available than what's physically in that system. So paging, and we'll talk about paging on Tuesday. They don't have to manage the shared memory space. So kind of like a hard drive. We have physical memory. It's going to be fragmented. It's going to be used by other processes. And so we don't, at the program level, have to manage how that is being addressed. The virtual address does it. There is a mapping between the virtual and the physical, and that's not something that we have to worry about. Here you can see a little diagram. Kind of shows that. Rip that off from Wikipedia. Virtual memory, you can see those different modules or different sections that map to the physical. They don't necessarily map to the same physical locations. They may even map to the hard drive, whether that's, again, a spinning disk or a solid state. But as far as a contiguous block of addresses to the program, it looks the same. All right, I think we should call it good there. When we come back, we'll finish talking about virtual memory. We'll get through the last of these slides for the PE and start talking about whatever else I said we were going to talk about. So, any questions at this point? Everybody's about ready to pass out. I know I am. All right, perfect. Well, have a good weekend. I'll see you guys on Tuesday.